Okay, so I'm just taking it back to the previous slide once. So just go through these equations we have just discussed about the acceleration of a particle in circular motion. Then we'll come back to the dynamical equations. Please let me know in case of any doubts with these equations. Hope the equations are clear so far. Okay, let's move back to the dynamical equations. So by dynamics, we mean the relation between force and acceleration. Okay, now if we talk about in particular uniform circular motion. Actually, you need to copy that first part. Okay, we'll come back to this. Okay, so let's come back to the special case of uniform circular motion. So as you know, by definition, uniform circular motion is when the speed of circular path is constant or the speed is uniform. That means the rate of change of speed is zero. So by definition, uniform circular motion is nothing but circular motion at uniform speed v. So that also means that angular speed omega is also uniform. So that also means that angular acceleration is zero, tangential acceleration is zero. So the net acceleration is nothing but the centripetal acceleration, or the net acceleration is minus omega square r cap, or minus v square by capital R. So now if we talk about dynamics, we'll see that therefore in uniform circular motion, the net force acting on the body is centripetal in nature. Therefore, the net force is of constant magnitude and pointing to the center at all times. So next up, we will understand it with an example. So suppose we have this situation: a particle of mass m, let's say m is equal to 200 grams, attached to a light thread of length 20 centimeters, is on a smooth horizontal surface with the thread attached on the surface at its other end. Now the particle is given a horizontal impulse such that it has a velocity of v equal to 5 meters per second perpendicular to the thread. Find omega and tension in the thread. Sorry, we'll find omega and we'll find the magnitude of acceleration. And the tension T in the thread. So just note down this section first. We will be applying this concept in this particular question now. So try to interpret the question and come up with a diagram for it also yourself. Okay, so let's try to visualize the problem first. So what is basically happening is that on some kind of a smooth horizontal surface, or frictionless horizontal surface. So imagine this is the like a tabletop or the surface of a carom board or something. This is actually horizontal. So this is a smooth horizontal surface. So gravity is pointing into the plane like this. Now on this, what we've done is we've taken a particle and attached it to a thread like this. So a particle of mass m is attached to a thread of length l, and the thread is attached at the other point. It's attached onto the surface at the point polars. So the thread is attached at the point O onto the surface, such that the particle can move in such a way that that point on the thread will remain fixed. So now we are giving the particle an initial velocity like this, perpendicular to the thread. So the mass of this particle is given to us as 200 grams. The length of the thread is 20 centimeters, and the initial velocity we are giving it is having a magnitude of 5 meters per second. So now we have to find the angular speed omega of the particle in circular motion as it moves. Then we have to find the acceleration of the particle. And we have to find the tension P in the thread. So let us say we are taking this as our y-axis, this is our x-axis. So our z-axis is the vertical axis. So the smooth horizontal plane is the xy plane. Okay, let's understand this question in detail. So what's happening here? If we see the top view of this system, you have the particle attached to this thread. Now the thread is attached to this point on the surface. So initially there is no tension in the thread, because what is happening initially, the particle is just lying on the surface, so its weight is balanced by normal reaction. The particle is at rest. So acceleration of the particle is 0, initial velocity is 0, and mg, which is into the plane, that is balanced by normal reaction, n, which is coming out of the plane. Okay, so we can't see those vectors in this diagram, but in that horizontal plane, we can see that mg is going into the plane, normal reaction is coming out, and those two balance each other, and the thread is not really tight, so its tension is 0. This is the situation initially. So I think this is pretty clear to everybody. Now see, the moment we give this an initial velocity, now the situation is going to change. Okay, so the moment we take it from here to where we have given it an impulse. So now we have given the particle a push or an impulse or like a jerk in this direction. So it has got a velocity v0 in the perpendicular direction to the thread. So what happens immediately when that happens? The tension develops in the thread. Because the particle has a tendency to move forward, so the string jerks and a tension develops. So the moment the impulse is applied on the particle, giving it a velocity or a momentum perpendicular to the thread will tighten up. The moment that happens, the thread tightens up. So tension becomes non-zero in the thread. Now the tension acts perpendicular to the velocity. So therefore, the tension acts like a centrifugal force. So it turns the velocity vector. So it turns the velocity's direction. But it does not change the magnitude. So we'll come back to the magnitude part. But the moment this tension acts, you can see now the velocity's direction will start to change. So what will happen is a moment later, the particle will have gone from this state to a state like this. The thread's length remains constant. So the particle is forced to go in this kind of path, in a circular path, where now the direction of its velocity is changing because of the tension acting perpendicular to the velocity vector. So this is where the particle started from at t equal to 0. Now a small time delta t later, it has turned through a small angle delta theta, like this. So just make a note of this section, or make sure you understand it. So in the three-dimensional picture, what is happening now is the tension starts to act like this on the particle. So it doesn't interfere with the fact that the weight and normal reaction are cancelling each other. So the vertical forces balance each other. But along with that, tension acts in the horizontal plane. Always perpendicular to the velocity and pointing to the center. Oh. So now taking all this into view, what we understand about the nature of the motion is that because the thread is fixed at the other end, the particle is constrained to move in a circular path. On the horizontal plane. About that point O, with the radius equal to the length of the thread, and tension acts to provide the centripetal force which is necessary to keep the particle in circular path by turning the velocity vector continuously. Now, there is no tangential force acting on the particle during the circular motion. Okay, the surface is frictionless, therefore. So, therefore, tangential acceleration is zero. Therefore, the motion is a uniform circular motion. Tangential acceleration is zero implies that the rate of change of speed is zero. Alpha is zero. So it has to be a uniform circular motion. Yeah, Harsh, because as you can see, the surface is frictionless, no? And there is no other external agent applying any force continuously. No? The thread cannot apply tangential force because the thread's direction is along the radius. No? And there is no other external agent. There is no friction. There is no other external agent. There's nothing else to provide the tangential force. The normal reaction is acting perpendicular to the surface, so it cannot act tangentially. Mg is acting into the plane, so it cannot act tangentially. So there is no agent to apply any tangential force. Had the surface had friction, then there would be a force acting opposite the velocity. That would create a tangential deceleration. But यहाँ पे friction नहीं है, it's a smooth surface. So experimentally, if you do this, you tie that particle to a thread and the surface is smooth. The particle, once you give it that initial velocity by giving it an impulse, its kinetic energy is not going to change because there is no force doing any work on it. It will continuously move in uniform circular motion with a constant amount of speed or kinetic energy. Is it clear now, Harsh? Okay, so now that we've understood that the path of the particle is uniform circular motion, I mean the path is circular and the type of motion is uniform circular motion. So if we visualize the top view, so we can understand that at any point of time, wherever the particle is, continuously the tension acting on it. When the particle is here, after some time the particle is here. After some time the particle is here. So as the particle is going in the circular path, continuously this kind of tension will be acting on it. So at any point of time, this tension will become mass into centrifugal acceleration, whereas normal reaction is cancelling mg in the vertical view. Mg is minus mg k cap. Normal reaction is plus n k cap. They cancel each other. This is our xy plane. So because there is no tangential force, there is no tangential acceleration. The particle only has centripetal acceleration, so it's in uniform circular motion. Its speed remains constant. There's nothing to accelerate or decelerate the speed. So hence we have this equation. Centripetal acceleration is minus v square by r. R cap. This is your r cap's direction. This is your tangential direction. So as the particle is going from point to point, there is always tangential, or there is no tangential force present. So there is no tangential acceleration. Okay, so these are the things that are given to us in the question. So using this, we can see that the angular speed is 10 radians per second, 5 upon 0.2. Oh, sorry, so it is 25 radians per second. And we can see that the acceleration is centripetal. It has a tremendous amount of acceleration. Actually, let's do one thing. Let's change the length of the thread. Instead of 20 centimeters, let's make the length of the thread something else. Let's make the length of the thread 5 meters. Easier to handle. So this should be 1 radian per second. Okay. So this is the net acceleration. Yeah, Priyanshu, if you just note it down from point to point, you will understand what's happening. So now we can see that the tension is equal to mass into centripetal acceleration, or this much. So the tension will become 0.2 kgs multiplied by 5. So the string will have a tension of 1 newton. Okay, so I'll just take you through the whole solution once more. Okay, let's look at another example. Next example we'll see is that of the conical pendulum. So it basically consists of a thread used to suspend a particle vertically from a given point. So again, the thread is attached to the ceiling at this point O. The length of the thread is L, let's say, and there's a particle attached at the bottom. So remember, when we say thread here, we assume the standard type of massless and inextensible thread attached at the point O. So we've done conical pendulum last time, is it? Just give me a second. Okay. So we'll skip the conical pendulum example. Just give me a moment, and yeah, we'll skip this conical pendulum example because we've done it last time. Now we'll move on to the next concept here. So we had seen a case of non-uniform circular motion also, and the dynamics of non-uniform circular motion last time. Now next thing we will look at is the concept of centrifugal force and a rotating frame. So the idea of this is related to Newton's laws, which you studied earlier. Just like when a body or a particle is in a non-inertial frame, it experiences pseudo force. So like that, when a particle or body is in a rotating frame, it experiences a type of pseudo force called centrifugal force. So when a particle or a body is in a rotating frame, for example, a block placed on the rough surface of a rotating disc. So imagine we have a disc like this. is rotating about this axis, and this is the rough surface, and we have a block or a particle or something like that which is placed on that rough surface, then this will tend to experience what we call centrifugal force. So when a particle or a body is placed on a rotating frame, it experiences a centrifugal force, which is a type of pseudo force. Radially outwards with respect to the axis of rotation of the frame. So this body here, this block, in the rotating disk will tend to experience an outward force like this, which is called the centrifugal force. So this is just like in a non-inertial frame, accelerating at a naught, a particle of mass m experiences pseudo force. Now you've done this in Newton's laws. What is the amount of pseudo force experienced by such a particle? Its magnitude will be m a naught, but the direction will be opposite to the acceleration of the frame. So it's something like that centrifugal force also acts. So the way we will relate it is just like how we related pseudo force from our everyday life experience, that when we are in a frame which is accelerated, then our body experiences a pseudo force in the direction opposite to the acceleration of the frame, or any other object or body that we see in that frame, it tends to slip opposite to the acceleration of the frame. Why? Because it experiences pseudo force. So suppose this is a vehicle which is accelerating at a naught like this, then a person inside the vehicle or an object kept inside the vehicle will tend to experience pseudo force like this. It is opposite to the direction of the acceleration of the frame. So centrifugal force is also something similar to that. From your everyday life experience, you know that if you are, for example, inside a car which is taking a sharp bend, it's in a circular path, then objects inside the car or even your body experiences a centrifugal force which is radially outwards. It's outward from the axis of rotation. So that is again what type of a force? It is a pseudo force. And why it acts? Because a rotating frame is also a non-inertial frame. So we'll discuss about the formula and the equation for it. Just note down this much first. Okay, now next thing, once we have got used to the idea of pseudo force, let us understand the expression for centrifugal force. So, for a body or particle of mass m in a rotating frame, angular speed omega, rotating at an angular velocity or angular speed of omega at a distance r from the axis of rotation. Okay. The centrifugal force has a magnitude of m omega square r and direction radially outwards. So we can say that as a vector quantity, it's like this. So you can understand that basically centrifugal force is minus of mass into centripetal acceleration. Because centripetal acceleration had the same magnitude, omega square r, but its direction was radially inwards. This one has a direction which is radially outwards. Just like for pseudo force, this is the relation. So if we are in a frame which is, or if a particle or body is in a frame which is rotating at angular speed omega, and there happens to be a particle or a body of mass m which is at a distance of r from the axis, then it experiences a centrifugal force in this sort of direction and of this kind of magnitude. Now, this m omega square r can also be written as mv square by r, where v is r omega. Okay, so hope this is clear. So now let us start looking at applications. So let's start with an example which is just like the case we sought to understand the concept of centrifugal force. So this is a wooden disc rotating about its vertical axis at constant angular speed omega naught, let's say, equal to 0.2 radians per second. Now on its surface, there is a particle of mass m, which is at a distance r from the axis. The mass of the particle is, let us say, 500 grams. Is at a distance r equal to 3 meters from its axis. The particle does not slip with respect to the disk surface. So first of all, find the particle's acceleration, magnitude of acceleration A, with respect to the ground plane, and make its free body diagram in the ground plane, which will be an inertial plane. The next, make its free body diagram in the frame attached to the disk. That's a rotating frame. And calculate the centrifugal force acting on it. Now, third part, from both free body diagrams, part 1 and part 2, find the contact forces, that is normal reaction and friction, acting on the particle, and the minimum value of coefficient of static friction needed to keep the particle at rest with respect to the disk. So this is the third part of the question. So just try this out. With this, the concept of centrifugal force and free body diagram, application of centrifugal force will become clear. Yeah, Aditya, you have to copy the part earlier. Okay, I'll take you to that. Okay, finish copying this, then we'll come back to the question. Okay, so let's work out this question now. So just make the two free body diagrams in part 1 and 2. We'll discuss that next. Okay, so let's work out these two parts. So what we can see that if we are looking at the particle from the ground frame point of view, so if we are a ground frame observer, then what we are observing is that we are observing the particle in a circular path like this. So our observation is that the particle of mass m is in uniform circular motion in a horizontal plane with angular speed omega and radius r. So what we will observe is that the particle during its circular path has a centripetal acceleration as the net acceleration at any point of time. speed of the particle is r omega. So when we make the free body diagram of the particle, what we'll see as forces acting on it will be normal reaction, weight, and static friction, because it is not slipping with respect to the surface of the disk. So static friction will be the centripetal force. That is a force pointing towards the center and providing the centripetal acceleration. Whereas normal reaction and mg cancel each other. So again, vertical forces, mg and normal reaction balance each other. So the net force acting on the particle is the frictional force, which is always pointing towards the center and having a fixed magnitude of so much. So now from the values we've written above, we can find out how much these contact forces are. So the angular speed was 0.2 radians per second. Mass of the particle is 500 grams and the radius r is 3 meters. We'll substitute those values here. So this frictional force, as you can see, this will have a magnitude of 0.5 into 0.2 square into 3. So it will be 0.06 newtons, whereas mg will be equal to normal reaction. So normal reaction will be, if we take g as 10 meters per second square, the normal reaction will be 5 newtons. So this is the first part where we are making the free body diagram in the ground frame or the inertial frame. Now next up, we will see the free body diagram in the non-inertial frame of the disk. Okay, let's come to the second part. So now if we are in the rotating frame, so let's say we are in a situation where our observer is present on this rotating disk. Okay, so we are in the rotating frame, which is a type of a non-inertial frame. So with respect to this observer, in the rotating frame, the particle is seen to be at rest. Okay. But remember, there is a centrifugal force acting on the particle, and that centrifugal force will be in this sort of direction, and that will be m omega naught square r in bracket. So that centrifugal force has to be balanced by friction. Whereas normal reaction and mg act in the vertical plane. So here what happens is, in the horizontal plane, centrifugal force of m omega naught square r acts radially outwards, and friction radially inwards, and they balance each other. In magnitude, they are the same. And in the vertical plane, vertically, normal reaction balances each other. Okay. So as you are seeing the particle going around in the circular path at any point of time, now the thing is, you are not seeing it going around in circular path. For you, the particle is always at rest, and on that there is centrifugal force acting always, and friction balancing that. Okay, so people hope this example is clear. Now we'll move on to our final example for today. Now in this, what is happening is that we have a structure like this. So an L-shaped pole, which is attached to a disc like this on the ground. At the end of the pole, there is a thread with a particle length is also L. So we have a metallic frame like this. Now what we see is after a while, the same structure is in a second situation. It is given a angular motion. So an external agent is making this whole structure rotate at constant angular speed. So this whole system is now rotating about this axis at an angular speed omega naught like this. And as a result of that rotation, what is happening is we observe the thread is like this. It is at an angle of theta with respect to the vertical. The particle is therefore describing a circular path like this. So this structure is now rotating at uniform angular speed. Omega naught, as shown. So if L is equal to 50 centimeters and theta is equal to 37 degrees and the mass of the particle is 2 kg, find the angular speed omega naught and the tension in the thread. How much is the tension in the thread? So this is the final problem we'll solve for today and understand the application of centrifugal force through this problem only. So just try this out. So what I would suggest you can do in the question is make the free body diagram of the particle in the frame of this structure, that is in the rotating frame. So with respect to that frame, that particle will be at rest, but there will be centrifugal force acting on it. Okay, so as I was saying, what we will do here is we will make the free body diagram in the rotating frame of the structure. So we are present in the rotating frame. So first of all, we will show that the particle experiences centrifugal force, which will be radially outwards with respect to This is the centrifugal force. And for that, we'll have to understand that the value of capital R or small r over W is this. So from the diagram, you can see that R will be equal to L plus L sine theta, because this is theta, this is L. So you can see that this distance here, this is L sine theta. So the total radius of the circular path, or the distance from the axis of rotation, small r, that becomes L plus L sine theta. And other than that, the forces acting on the particle are the two standard physical forces of weight and tension. So tension and mg, and tension is at an angle theta to the vertical. So we can see that T cos theta balances mg, and T sin theta balances m omega naught square r. So from this we will get both the things required. Now theta is 37 degrees, L was 50 centimeters. So R will become 50 plus 50 into sine 37, that is 3 by 5. So 80 centimeters or 0.8 meters. That will be the value of R. And the mass of the particle was 2 kilograms. G is 10 meters per second square. So from equation 1, you can see that tension is mg by cos theta. So it is 20 divided by 4 by 5. Or the tension is equal to 25 newtons. And if we divide equation 2 by equation 1, you can see that tan theta is equal to omega naught square r by g. So omega naught is square root of g tan theta by r. So that is square root of 10 into 3 by 4 divided by 8. So this is our value of omega in radians per second, which we will solve further in just a moment. So that is square root of 15 by 16, right? So root 15 by 4. It's very close to 1.98 radians per second, something like this. Okay, so these are the two values. So hope this is clear to all of you. And with this, we complete today's session. So I'll be sending a list of questions to do from HC Verma. In the main exercise, do questions 1 to 12. We'll discuss some of these questions in the next lecture also. And also go through the concept of banking of a circular road. It's there, the theory part in HC Verma, and banking angle. We'll be discussing about that in the next lecture also. So that's it for today's session, people. Wish you all the best.